Hello, welcome back. This video starts a short series of videos that's focused on imaging and really in the radiation therapy context. But I'm going to try to give a basic overview as deeply as I can. So the topic of this video is radiographic imaging, and that's taken to mean anything that involves imaging with an X-ray. So I'm going to focus on the principles of that, and I'm going to be talking about, planar X-ray images, what you traditionally think of as an X-ray. But a lot of what I say is going to apply to CT imaging, which is the topic of the next video. And some of it will also apply to other imaging modalities. I'm going to talk about informatics and how data is stored, and that applies across the board. So here we go. I'm going to start by talking about contrast. So let me start by drawing a source here. And you'll remember what the source looked like. That's an X-ray tube, right? And you can go back to video 8.1 to review that. So you have an electron accelerated towards an anode that produces a photon, and there's your source, the spot there. And it has some finite size. So now we're going to image something. Let's say it's an arm, and there's a bone inside, and we're going to image it with a detector. Some kind of detector, and I'm going to talk about detectors in a few minutes. So now let's consider two photon ray lines, one coming through the bone and one through the soft tissue, the muscle, let's say. And to understand that and what the math of this, let's make a cartoon here. So here's thickness of tissue, and photons come in, and they have some fluence of I0, and what comes out is fluence I1. And the thickness of this tissue is going to be 10 centimeters in this example. So you can go back and review how to do this calculation, but you probably remember. Here's the equation for the transmitted fluence, e to the minus mu x. So I can write this I1 over I0 is equal to e to the minus, now I'm going to have to go look it up. So here's the NIST website. I'm looking up muscle here, and I'm going to have to pick an energy. So I'm looking up mu over rho here. And you'll see it's 0.3783 at 30 keV. That's mu over rho. And so I multiply by the density, 1.05 times 10 centimeters. So let's type these in and plug and chug. And you see it's 0.0188. So let me write that here. All right, so now let's do the same calculation, but instead, I'm going to put the bone in there, and it has a higher density and a different attenuation coefficient, and let's say that's 2 centimeters thick. So it's the same calculation, I0 in, and now I'm going to call this I2 coming out, and the first part is exactly the same, so it's e to the minus mu over rho times the thickness, which is 8 centimeters here. And then now I'm going to have to multiply by the attenuation in the bone. So let's look that up. We go to bone. I'm going to use cortical bone. Again, using 30 keV. So the mass attenuation coefficient there is 1.331. You can see it's quite a bit higher. So write that here, 1.331. And the density for cortical bone is 1.92. And the thickness is 2 centimeters. So let's type that in here. Okay, and this is now 8 over here. So it's 0.00025. All right, so now let me take the ratio of these two. So I1 over I2, and that is actually 74.8. So this then is what we mean by contrast. You can see the number of photons coming out through the muscle is 74 times higher than when you have the bone in place. And so you can see the difference between these two. Rays coming through, the bone's more attenuating, and so it's some measure of contrast. So now remember, everything I did here is at an energy of 30 keV. I assumed a monoenergetic beam to look up the values, but what happens if we change the energy? Let's change it a little bit, down to 25 keV. And we can do the same calculations, so I1 over I0. I'm not going to look up all the numbers, but if you do, here's what you get. And I2 over I0, the number is 2 times 10 to the minus 7. So both numbers are smaller. Let me take the ratio of these two again. I1 over I2 is 7,928. So this is some measure of contrast, right? The difference between these two. And you'll see that the contrast is much higher at the lower energy than it is at the higher energy. So that should make sense. If you look at this graph of the cross sections, mass attenuation coefficients, you can go back and review this in these videos if you need to. But if you look at low energies here, especially the difference in attenuation in high Z material versus low Z material, say water or mussel, is much different because of the photoelectric enhancement. That gives you the contrast. So while we're on this topic of energy dependence, let's look at what happens up in the megavoltage range up here. This is relevant for imaging with a linear accelerator. And you'll see that there's almost no Z dependence. So in other words, the mass attenuation coefficient of titanium or bone or water is about the same. So let's look at how that plays out in terms of imaging. Here are two images. On the left, a megavoltage image from a LINAC, and on the right, for the same patient, a kilovoltage image. And you'll see the contrast is much better for the kilovoltage image, and that's because of that extra Z-dependent enhancement. Now you see the bones on megavoltage image just because they're more dense, not because the mass absorption coefficient is higher. So contrast is one dimension of image quality, the bone or other tissue standing out against this background, but there are other dimensions as well. And so let's talk about the next one, which is the resolution of the image. So the image should be sharp and not blurry. So let's talk about what makes an image sharp or blurry. So the parameter we're talking about is resolution, spatial resolution. So to look at that, I'm going to draw a ray line here, and it's going along the edge of the bone. And what you want for high resolution is essentially to have a sharp edge, to have a sharp image on the detector. So what controls that? Well, first of all, it's the geometry. So let me label these so we can understand it. So this top distance is A, bottom distance is B. And we can think about this in terms of penumbra. So video 9.1 will explain this. You can review it if you want. It's kind of like the effect of an edge, or how sharp an edge is. So you'll remember the penumbra is proportional to the S, the source size of either the LINAC or in this case the X-ray tube, times B divided by A. So that's going to tell us what the resolution is. As I change these parameters, it will change. This is closely related to another parameter, which is magnification, M. So let me walk through what that is. In the patient, this object has some physical size, let's call it little r. And then if you draw a ray line down here onto the detector, you can see it's much bigger on the detector. So I'm going to call that big R, the dimension of the detector. So by similar triangles, I get R over A is equal to big R over A plus B, right? And I can rewrite that. Big R over little r equals A plus B divided by A. And I can simplify that. So 1 plus B over A. And this thing here is called the magnification, or mag. So let me rewrite it down here. So you'll see that mathematically and geometrically, these quantities are related to each other. So let's look at how this plays out in an example. Let's move the patient a little bit. We moved it up, move them up towards the source. And then you'll see now if I draw these lines that the magnification is much larger. It's bigger on the detector. But also the resolution is worse, right? Because we're closer to the source. What I call the penumbra is bigger. The B is larger. That sort of makes physical sense. So in this example here, the mag goes up and the resolution goes down. Now let me focus in on this part of the system, the detector. That's going to affect both the contrast and the resolution of the overall system, so it's very important. The detector can be something simple. It could be film. But a lot of the detectors that we see in the clinic now are electronic and they provide real-time readout. So I'm going to focus on those. Here's an example of a detector in the therapy context. Actually, two of them. This is the electronic portal imaging device. We call it the EPID. And in this system here, you'll see two detectors, one for the megavoltage beam, MV, on the bottom, and one for the kilovoltage beam, which goes sideways, kV. So let's look inside and the detector and see, and we'll use the MV detector as an example. I'll go through how this works, but what you see is you have these different layers. In this system, you have an aluminum cover, a copper conversion plate, and then the active layers at the bottom, the green and red, that I'll go through in a minute. So you have a photon coming in, and that photon could go in directly and interact with the scintillator, but more often it's converted in this conversion layer to an electron through Compton scattering, and then it goes into these active layers. So let's look and focus in on these layers where the image is created. So you have a scintillator layer, the green, and this is typically a rare earth, like for example, gadolinium oxysulfide. And what happens is that when you have a charged particle interacting here, it emits light. It emits photons, optical photons. And they come out through the layer, and then they are registered or detected in the system below it, the photodiode array, typically made of amorphous silicon, and that provides some readout of the charge from number of photons that are coming out. So let's look in more at this photodiode array layer. So here's the instrumentation. You see there's two lines coming out, a gate line and a read line, and here's the silicon, and it's all connected to a TFT. And there are many of these, right? So I'm kind of just showing a couple of them, but it comes in an array. They're very, very small pixels, and each are instrumented. So you have these lines going across. Those are the gate lines, or the row, and you can control which row you're reading out. And then going down, you have the readout lines. And each one of these is instrumented with electronics, and you read the data out one by one as you go along down the rows. So in the end, you have this map. You have pixels, we call them. The image is broken up into pixels. So you might have n by m pixels. And there are many, many pixels, usually millions. For example, you might have an image that's 1024 by 1024. Now, these pixels are going to affect the resolution of the image. So let's look at this through an everyday example. You remember these guys. They made a guest appearance in some of our videos, the kids. So this is a nice high resolution image, lots and lots of pixels. But what happens now if we reduce the number of pixels in this image? So let's look at that. So factor of 2 fewer, 2 more fewer, have it again, you can see the resolution is getting much worse until you almost can't see the image. So clearly, pixelation is affecting image quality, but there are other factors as well. Remember back to this image that the resolution is affected also by the size of the source. That's a big factor, and where you have the patient as well. So there are quite a few parameters that affect resolution. All right, so by way of review, I've talked about contrast in this video, and I've talked about spatial resolution and the parameters that control that. And the last image quality parameter I want to talk about is noise, which is very important for medical images. So let's go back to the example to see how that works. So we'll take this image, turn it into black and white, because that's usually what we do in medical images. And I'm going to keep the resolution the same, the spatial resolution, but I'm going to add noise to it. Here you go. So you can see that it's much harder to visualize. So let's talk about noise in the context of X-rays. So if we look back here for how X-ray images are generated, there's going to be two important sources of that. So one is the number of photons, n photons coming in per pixel. And that's going to impact the noise. So because this is a random counting process, and you've got n photons on average coming into that pixel, but how many you observe is going to is a random process, and so let me describe the mathematics behind that. We're going to have to look at the Poisson distribution. So Poisson distribution is the mathematical description of a probability of measuring k events given that the average number of events, is big N. So you can write this like this: e to the minus n times n to the k divided by k factorial. I'm not going to derive that, but n here's the mean number of events, or in this case, photons, mean number of photons in that pixel. And we can look at what this looks like graphically. So let me plot here the probability distribution. So the probability of observing k photons as a function of k. And here's what this looks like for an average number of photons of 1. And you see it's bunched up near 0, and there's some chance of observing 0 events and some chance of observing more than 1 event because it's a random process. So here's for another value. Here's for n equals 4, average number of photons 4. And again, you can see it's shifted, but again, sometimes you get 0 and sometimes you get more. And here's for n equals 10. And you can see that it starts to approach a Gaussian distribution, which is central limit theorem. Now, the standard deviation of this probability distribution is important because that tells you how wide it is, so how much noise is going to be. Standard deviation is equal to the square root of n for a Poisson distribution. I'm not going to prove that, but it's easy to prove. Okay, so now we can look at an important property, which is the ratio of the signal in the imager divided by the noise. And the signal is going to be n, because if you measure on average n photons, and the noise is square root of n, as we just were seeing. And so this ratio, it goes like the square root of n. This is the signal to noise ratio, SNR, which is a very important parameter. What you see is that if you have more photons coming out, the signal to noise ratio gets bigger. So the image will be less noisy for more photons. So how do you get more photons onto a detector? Let's look at that. One way to get more X-rays at the detector is to get more X-rays out of the tube. We studied X-ray tubes in video 8.1. You can go back and look at that. You'll recall that you can get more photons out by just increasing the current in the tube, the number of electrons per unit time, the MA. Okay, that shifts the whole curve up and down, the whole spectrum up and down. So exposure then is going to scale linearly with MA, with the current in the tube. Another way that you get more photons at the detector is to have more penetration to the patient. So that's either a thinner patient or a spectrum that's harder. So harder here, the green versus the blue, for example. Harder spectrum is higher KVP, and so the number of photons is going to go up with KVP. It doesn't go linearly with KVP, though. It goes as some power, and that's a little hard to understand, but the exposure at the skin is proportional to KVP squared, but the exposure that's transmitted through the patient usually scales differently, approximately as KVP to the 5th power, but some authors are claiming the scaling is closer to KVP to the 4th power. But it depends on the patient. Okay, now another thing that controls the signal is down here, what happens in the active layers, and also in the conversion. So you'll see more than one photon is coming out in the scintillator, and if you get more photons out, or better absorption in the conversion layer, then you're going to have a higher signal, right? So you can make this conversion area thicker. You can maybe make the scintillator thicker. You could change the type of material of the scintillator. That would give you more of these photons out, more signal. Overall, this is called the detective quantum efficiency of the system, DQE. Essentially, how much signal comes out. I talked about one way to influence that. You can make the collection conversion layer thicker, okay? But there are disadvantages to that. as well. So a thicker area, you're spreading out the collection area over a bigger range, and so that essentially blurs out the image, makes the resolution lower. So there are trade-offs like that, and that can be quantified through this thing that I'm not going to get into, but it's called the modulation transfer function, which is essentially describing the responsiveness of the detector as a function of the frequency of images that you're trying to resolve, so that the spatial frequency. So now I'd like to look at the effect of scatter on image quality. So scatter is interesting because it will increase the signal in your image. You'll get more photons, but they're not useful photons, so it actually won't help you with the contrast. So it's sort of another dimension that we have to consider when we're looking at image quality, kind of conjugate to the signal to noise ratio. We could talk about the contrast to noise ratio. So let's look at how this plays out. So the goal of distinguishing contrast is to be able to tell the difference between the attenuation along these two ray lines, right? That's the goal of imaging contrast. So remember now that the field is quite large, though. And so because of that large field, you get scatter of photons from different parts of the field towards this pixel of interest. And so that scatter is an extra signal, an unwanted signal, that doesn't give you any information about what's inside the patient. It's just sort of a background fog. More photons, but they're not useful photons. Now, if we consider this geometry where we move the patient up, what you see is actually the scatter conditions are a little different. So if you have photons scattered here, it goes out and it doesn't reach the detector, right? So you get less scatter at this position. So the scatter component is affected by the geometry. It's also affected by the thickness of the patient. Smaller anatomical region will have less scatter, and it's also affected by the field size in the two dimensions. Now, there's another way also to control scatter, and that is to use a thing called a grid, anti-scatter grid. So let me try to draw what that looks like. You have these little slits. They're little pieces of metal, and they're arranged exactly so that they point towards the source. They diverge back towards the source. So any photon coming in along the line that's directly to the source, it'll get through. But if photon's scattered that comes in at some sideways angle, it'll get stopped by the grid and it won't make it to the detector. So this grid then acts to reduce the scatter photons. All right, now I'd like to talk about how images are stored and viewed and transferred between systems. And the protocol for that is DICOM, Digital Imaging and Communications in Medicine. This is a very important concept. It's the way that images are handled. So let me do this and help you understand it by going through a brief history of how DICOM came to be. So let's consider where this started at first. All medical images had their own format, vendor-specific format, so the systems couldn't talk to each other. There was no common platform. So that was the early 80s and prior. So that's a kind of ancient history. Like my kids will ask me, Dad, tell us about the old times, like the 1980s, like when there were dinosaurs. I'm like, how old do you think I am? Well, then in the mid-80s, the American College of Radiology and NEMA, that's the National Electrical Manufacturers Association, they started standardization initiative to try to organize this, bring some order to it. In 1985, the first standard was published for DICOM, and it slowly caught on with the vendors. It took some time, but basically by 1993, there was really good buy-in. They changed the name to DICOM, and it was published as a NEMA standard, DICOM 3.0, and that's what we use today. And when they want to modify it, they publish a supplement, they call it, to extend it. You'll also encounter the term PACS. That means Picture Archiving and Communication System. So that's not a communication standard like DICOM. It's more of a system. So like, for example, the hospital will have a PACS system. That might be the radiology PACS that serves the radiology images. So PACS can use the DICOM standard to communicate between it and other systems. Now, in the radiotherapy context, an important development was DICOM RT. So that was an update, an extension for RT, radiotherapy objects. Those included the structure sets, so contours, the RT plan, the RT dose, the RT image. The RT image could be like a DRR or a radiograph. And this standard supplement was published in 1996, and it's become very useful. It started to be used in trials in 2003, and then by 2013, the NCI required that it's used in all trials. So it's also very supportive of the trial structure. Now, that's being updated, and there's like basically the new version of DICOM RT, future version, and that's a work in progress as of now. But here are a couple of things happening. So there's going to be a DICOM supplement that's going to cover physician intent, so prescription, dosimetric objectives, and a new way to handle structures with annotation and logic, like expansions and so on. There's another DICOM supplement that's going to be dealing with region of interest templates, standard structures per disease site, and some other things. So these are like the new version of DICOM RT coming out soon. It might be useful to look at some of the software packages that can be used to view DICOM. And here are some. This is a very short and subjective list, but these are some of the packages that I've used that I like, mostly freeware. And you can see the link here to download. So you can download these and use them to view DICOM images and the information in them. Also, there's this publicly available data set from the Cancer Imaging Archive that's supported by NCI, and here's the link for that. It uses the data retriever, which is a piece of software they've written. And so here's a taste of what the website looks like, some introduction, and then you'll see there are different studies here that you can download by disease site. It's got CT, MRI, ultrasound, radiographs, PET, etc. Many thousands of patients, and they're all annotated too with radiology reports and everything. So it's an incredible wealth of data that's being used for many things now. I thought you should know about it. So here I've downloaded some images from TCIA and into DICOM browser to look at them, and I think we can just have a look and you'll understand DICOM a little better. So these are CT studies from a lung cancer patient. And here's the DICOM header. You can see these tags. See the tag? It's a word that describes metadata for that scan. So here you see the modality. It's CT in this case. You can also see when the scan was acquired, what the scanner it was on, and a lot of other data here as well. And you can see even more when it's not anonymized, obviously. But so have the patient's name, ID, birth date, demographic information. You can also see parameters about the scan itself. So if we scroll down, you can see the slice thickness of the CT, the KVP that was used, and down here I think we can see the MA, X-ray tube current, and other parameters of the scan. So there's lots of useful information here for interpreting the study. Now we can also view the image. So look, you'll see this particular CT slice. It's 512 by 512 pixels. You can adjust the imaging. DICOM browser is actually using ImageJ to do this. So there's lots of tools that come with that. You can measure pixel values, draw regions, etc., etc. Okay. All right, so those are the basics of X-ray imaging. I'm going to leave you with this reading list. There's a lot of resources for looking at imaging and medical physics, but these are some of them. Now, in the next video, we're going to get into CT imaging, which takes a lot of what we just learned in this video and applies it to a 3D imaging modality. We'll see you in the next video.